Alright, you should have your packet out, just like you always should have your packet out. And in your packet, you will want to be turned to that worksheet right there. Looks just like this. And then you could also have your PowerPoint open, ready with your stylus to take notes. Alright, so we're going to talk about light and the electromagnetic spectrum, which means we need to talk about waves. First thing you need to know about waves is that all waves transfer energy. All waves transfer energy, no matter what kind of wave it is. Whether it's a wave at the beach, or a sound wave, or a light wave, or an earthquake wave, all waves transfer energy. There's two categories of waves typically, which is mechanical waves, and those types of waves require a medium, something to travel through. Like water waves, well, they travel through water. Sound waves, you must have some kind of solid, liquid, or gas for sound waves, some kind of matter, some kind of medium for sound waves to travel through. And then earthquake waves obviously travel through the ground. Whereas electromagnetic waves do not require a medium. They can travel through space. And in space we have a vacuum, which is where we have not considered matter. So it's not a solid or a liquid or gas. It is kind of almost matterless, so to speak. In space, sound does not travel in space because sound needs a solid, liquid, or gas to travel through. But light, however, being an electromagnetic wave, can travel through space, and we know that because light reaches the Earth from the sun. So light must be an electromagnetic wave. It has to travel through space. It is important to note all electromagnetic waves, because we're going to talk a lot about electromagnetic spectrum today. Remember, that's the title here, electromagnetic spectrum. All electromagnetic waves, EM waves, have a speed of 3 × 10 to the 8th meters per second. And so they all have that in common. Waves can also be categorized as either a longitudinal wave or a transverse wave. Longitudinal waves can also sometimes be known as compressional waves. And an example of a longitudinal wave would be sound. Sound is a longitudinal wave. It's kind of like if you were to sit on the floor with a slinky and one person at one end and the other person at the other end and push that slinky, you would see something happen like this in this picture, and you would see compressions and you would see where it's not compressed, and that's called a rarefaction. And then there's transverse waves, and this is more like if you were to get a jump rope and have one person on one end and the other person on the other end, and you're moving that jump rope up and down, you would see something that looks more like a transverse wave, this wave right here. Transverse wave would be a light wave, is an example of a transverse wave. And because, again, I'm going to bring you back to the very beginning slide, we're talking about electromagnetic spectrum, and light is the title slide here, we are not going to focus on mechanical waves. We are going to instead focus on electromagnetic waves. So we're not focusing on this stuff up here. But you need to know that there are two types of waves. And we are not going to focus on longitudinal waves or sound. We're going to focus on electromagnetic transverse waves or light. You should remember from previous science classes how to label a transverse wave. You should remember that the bottom of the wave is called the trough. The top of the wave is a crest. If you were to measure either from crest to crest, because we got the top of a wave here, top of a wave here, if we measured from crest to crest, that would be a wavelength. Or if we measured from trough to trough, this would also be a wavelength. And wavelength a lot of times is denoted by an upside down looking Y, and that that symbol represents wavelength. And then finally, amplitude is from midline of the wave, not bottom to top. This right here is not amplitude. Do not get that confused. It is from midpoint of the wave. Okay, as if I drew a line, cutting that wave in half. Midpoint up to the trough, or you could also say amplitude is midpoint, midpoint up to the crest, or midpoint down to the trough. Either one of those would be considered amplitude. Okay, so electromagnetic spectrum. It basically represents the range of energy from low energy to high energy. And low energy is where we have radio waves, and high energy is where we have gamma waves. It also represents from long wavelength to short wavelength. And down here is a wonderful picture of the electromagnetic spectrum. And you just learned that a wavelength, or you should have reviewed that a wavelength is from crest to crest. So you can see over here with radio waves, we have very long wavelengths. So that's a very long wavelength. But over here near gamma waves, look at how short they are. That's a very short wavelength. So you can see as you go from radio wave to microwave, infrared, visible, ultraviolet, X-ray, and gamma rays, the wavelength gets shorter and shorter and shorter and shorter as you go. We're also going to talk about how energy and frequency get greater and greater and greater and greater as you go from radio to gamma. So radio waves are first. Those have the longest wavelengths and the lowest frequencies. And frequency is the number of waves that pass a certain point per unit of time. So this, when we talk about frequency, we're talking about number of waves per second, because we measure SI unit time in seconds. So the number of waves that pass a certain point per second would be the frequency. And you can see here in the entire electromagnetic spectrum, you have very few waves passing a point per second. But over here, you have a lot of waves passing the point. So we have a very high frequency over here near gamma, and a very low frequency over here near radio and microwave. So radio waves have the longest wavelength and the lowest frequency of all the electromagnetic waves. And yes, these are all electromagnetic waves. Radio, microwave, infrared, they're all considered electromagnetic waves. That means they're all transverse. That also means that they all travel at the exact same speed, 3 times 10 to the 8 meters per second, which we talked about on the above slide. As we go, let's go ahead and also fill out this worksheet here. So we know radio waves are way over here on the spectrum with the longer wavelengths. Okay. Microwaves come next. They have wavelengths that can be measured in centimeters. The longer wavelengths of microwaves, closer to a foot in length, those are the waves of which we heat our food in a microwave oven. So microwave on the electromagnetic spectrum comes next. And yes, you do need to know these in order. Infrared waves have even a shorter wavelength and higher frequency than microwave, so those come next. Infrared waves come next. And infrared waves, examples of those, heat lamps give off infrared waves, and people give off infrared waves. You could see that if you had a thermogram image of yourself. So you do give off radiation in the form of infrared waves. Visible light is next on the spectrum. And visible light is the part of the electromagnetic spectrum that we can see. So it's the only, because you cannot see microwaves, you can't see the waves happen inside your microwave. You can't see radio waves travel to your radio, but you can see visible light. And you see visible light in colors. And we know those as Roy G. Biv. Red, orange, yellow, green, blue, indigo, violet. And of Roy G. Biv, red has the longest wavelength, and violet has the shortest wavelength. So on your diagram, it already tells you visible comes next after infrared. So we know this is red, orange, yellow, green, blue, indigo, and violet. And this all fits kind of right here in this section in the visible light. And you can see, if you look at the wave diagram, it makes sense. Red's over here, it's got a longer wavelength, or lower energy, lower frequency. And over here, violet is closer to this picture of a wave. It has a shorter wavelength or a higher frequency, higher energy. Ultraviolet waves come next. They have even a shorter wavelength and a higher frequency than visible light. So here we have ultraviolet waves. Those come next. And ultraviolet waves can be used to kill bacteria, so we use them to sterilize equipment sometimes. If you have too much UV rays, this is why we put on sunblock. It can cause skin cancer. So I know UV rays get a bad rap, but even though UV rays get a bad rap because they can cause cancer, you don't want to get no UV rays at all, because UV rays are good because they also cause your skin to produce vitamin D, which is good for your teeth and your bones. And without it, you would have to take a lot of extra vitamin D. UV rays are also good because they are used by insects to locate nectar, so we can pollinate. X-rays come next on the spectrum, so we're going to put that next. X-rays. And you're familiar with X-rays. You might have had an X-ray once or twice in your lifetime. And these have even a shorter wavelength than UV rays. They carry a greater amount of energy, and they can penetrate matter. And because they can penetrate matter, this is why at the doctor's office you're given an X-ray if they want to see your insides, because the X-ray is absorbed by teeth or bones. So it's the light part of an X-ray image that indicates where the X-ray was absorbed, so that way a doctor can see what's happening inside. However, too much exposure can cause cancer, which is why, because it has such high energy, it can cause cancer, which is why your doctor or your dentist are going to provide the lead vest for you, so that you're only getting exposure of an X-ray where you need that exposure of the X-ray. Gamma rays are last on the electromagnetic spectrum. They have the very shortest wavelength and the highest frequency and the greatest amount of energy. Because they have the greatest amount of energy, we're talking greatest amount of energy, shortest wavelength, highest frequency. Because of that, they can penetrate almost all matter. Gamma rays can even penetrate lead. A lead vest is not going to stop a gamma ray. Gamma rays are used in radiation treatment to kill cancer cells if you already have cancer. but gamma rays are also used in exploding nuclear weapons because they are so harmful. So this would go last. Gamma rays go last. So this kind of summarizes what we've been talking about. These are all radio, microwave, infrared, visible, ultraviolet, X-rays, and gamma rays are all part of the electromagnetic spectrum. Notice visible includes the Roy G. Biv, the colors. If you were to draw your wave, you would actually draw the longest wavelength over here, and as you go, the wavelength gets shorter and shorter, and you notice you're going to more frequently draw more frequent waves until you have very short wavelengths over here. So we go from a long wavelength, remember wavelength is from crest to crest or trough to trough, to very short wavelengths over here. Long wavelength, short wavelength, going from radio to gamma. Or you could say we go low frequency, meaning the amount of waves that pass a certain point per second would be not very many waves per second. Whereas over here, we have a lot of waves happening per second, so we would have low frequency at radio and high frequency over here at gamma, and it kind of goes from radio to gamma. And you could also say you have low energy over here at radio, and you go to high energy with gamma. On your worksheet, you need to indicate that. So over here, with radio waves, we have a very low frequency, and over here on this side of the spectrum we have a higher frequency. Over here we have very long wavelengths, and over here we have very short wavelengths. I also want you to indicate that we have a low energy on this side of the spectrum, and we have high energy on this side of the spectrum. So go ahead and write that in on your chart as well. So on a quiz or a test, I could ask you these questions. It says, what color is the highest energy visible light? So you would have to know this spectrum to answer that question. It's asking, what color is the highest energy visible light? Well, we know we have a higher energy on this side of our spectrum, higher energy. So the highest energy light has to be over here on this side. That would be the violet color over here. Let me erase that. So we have that violet color right there would be the highest energy. If I had asked you which color has the lowest energy, you would tell me red has the lowest energy. It's closer to this side, the lower energy side. I want to know next, the shortest wavelength of electromagnetic radiation is. Okay, so go back and look. Here we have long wavelength, and we go all the way to short wavelength over here. So that means the shortest wavelength is on this side. That would be a gamma ray. The next question. The wavelength of a wave, and you've got two choices, increases or decreases as the frequency increases. So here we're looking at a relationship between the wavelength and frequency. So it's asking, what happens to the wavelength if the frequency increases? So the frequency increases this way. We go from low frequency to high frequency. So the question was, what happened to the wavelength? And again, here's your wavelength. As you go from low frequency to higher frequency, notice the wavelength gets shorter. So the answer would be the wavelength decreases. As wavelength decreases, what happens to energy? Does it increase or decrease? Okay, wavelength decreases. We get shorter and shorter and shorter wavelength as we go from radio to gamma. It's asking what happens to energy. Well, as we go from radio to gamma, we get higher energy. So energy would increase. And then, as frequency decreases, what happens to energy? So let's go back and look. As frequency decreases, you got to think, which way do we go as frequency decreases? Well, we've got lower frequency here and higher frequency here, so frequency decreases in that direction. We go from high frequency to low frequency. We're decreasing in frequency, and that's what the question was asking us. So then what happens to energy as we go that way? Well, as we go this way, notice we go from high energy to low energy. So therefore energy also decreases. So you can tell that based on the types of questions asked, and these are the types of questions that could be asked on a quiz or a test, you would have to know your electromagnetic spectrum in order, and you would have to know where you have long wavelength to short wavelength, low frequency to high frequency, and low energy to high energy in order to answer those types of questions. In fact, on a quiz or a test, you may even want to jot down, like, go from your head and just go ahead and write this stuff down and draw yourself a picture, so that way when you get to the questions like that, you can easily just look and reference your picture and be able to answer those questions. Later on in the ground state, excited state video lesson, you will go through the remainder of the PowerPoint, but I'm going to stop here.